Hello and welcome to our lesson on the equations of lines in R2, so in 2 dimensions. You should be familiar with the fact that we really already know a couple of forms of equations for lines in R2, right? If you have a line on the xy plane, you know that the equation of a line might look like this: y equals mx plus b, which is what we call slope y-intercept form. Right, where m is the slope, b is the y-intercept. You should also be familiar with the concept of the standard form, so it's just a rearrangement of this, where you have all the terms on one side of the equal sign and the other side is equal to 0. So we call that standard form. We're actually going to give that one a new name in a bit, but for now we'll call that standard form. And another form you might not be as familiar with, but sometimes we'll talk about, is what we call slope point form. So it's very similar to slope y-intercept form, where in slope y-intercept form you have the slope and the y-intercept, but slope point form you're using the slope and just a general point. So it's still y equals m, but now it's x minus a plus b, where AB is a point on the line. So this could be any point AB on the line. Okay, so those are the equations that you should be familiar with. These two for sure, maybe this third one. If you're not, it's not a big deal. Actually, we've kind of seen this before. This is really just comes from this, the fact that m is equal to the difference in y's, y minus b over x minus a. Really, you should be familiar with this, right? That's just the equation of the slope of a line. Well, if we rearrange that, right, cross multiply, m times x minus a is equal to y minus b, and then just add b to both sides, so plus b, then we'll get y equals m x minus a plus b, which is that, right? So it's really just the slope of a line rearranged. Okay, so these are the forms you should be familiar with. Okay, so now what we're going to do is look at new forms of equations of line, taking into what we know about vectors. Okay, so we want to consider this line with the slope of a half passing through the point -3, -2. If you're doing this in the other form, let's say y equals slope point form would be the best to use here, x minus a plus b, then the point AB, so a is equal to -3, b is equal to 2, and m is equal to half. So it would just be y equals 1/2 x minus a, so minus -3 would be plus 3 plus 2. So this is your slope point form. So then just by expanding and rearranging, you could get into the other two forms. So, I mean, it's easy to do that form. But now we're going to look at what we call another form of the equation of a line. So let's graph this line. So how do you graph this line? Well, we need a starting point. So our starting point is going to be the point that we were given. So we know that this line passes through negative 3, 2. So that's this point right here. So we know our line's going to go through here. Negative 3, 2. We know it's going to go through it with the slope of 1/2, meaning the rise is 1, the run is 2. So a rise of 1 means you go up 1 unit, and then so up 1 unit over 2 units. Up 1 unit over 2 units. This is 1. Okay, so it's this line right there. Very rough sketch of this line here. Okay, so now we're going to ask the question, what vector in standard position is this line parallel to? So if you remember, a vector in standard position means it starts tails at the origin, and then its head will travel in this direction, and it'll need to be parallel to this. Well, we're going to find this vector in the same way we found this, right? The slope of this was 1 over 2. So if this is going to be parallel, the slope must be 1 over 2. So it must go to this point. So what vector is that? Well, that's just the vector 2, 1. Okay, so we're going to call this vector M. So 2, 1. So this is what we'll call the position or direction vector of this line. So now I might ask you the question, is this the only direction vector? Is this the only vector parallel to this line? And hopefully your answer would be no. There's lots of vectors parallel to this line, right? Any multiple, right? If I extended this, doubled the length, 2, 4, 2, that's still parallel to the line if I went in the other direction. So in the negative direction, negative 2, negative 1, still parallel. Any multiple of this. So really, t times m would give you a general vector parallel to this line, where t is any number, any real number. Okay, so that's your direct vector. This is going to form part of our new equation for the line. Right? T times this vector 2, 1 gives us all the vectors along this line. The problem is we're not talking about this line that goes to the origin. We're talking about this line that's up here. So what we're going to do is kind of reposition this vector. And I'm going to reposition. So what I'll do is, instead of starting at the origin, I'm going to move this point to here. So all I need to do is add negative 3, 2 plus t 2, 1. And this is my new equation, where the first coordinate would be x and the second coordinate would be y. Okay, so this is what we call the vector equation. So all an equation really is an equation of a line is an equation which will generate all the points on the line. And that's exactly what this will do with different values of t. For example, if t was equal to 0, then xy, you just put 0 in here, then xy would equal negative 3, 2. That's this point. That's your sort of starting point for this line. Then as we change t, it's going to move us along the line. If I let t equal 1, then xy would equal, I put 1 in for this, and then I would get negative 1, 3. So that would be this point right here. If I let, you could do in between, right? If t was equal to half, t equals 0 was here, t equals 1 was here, t equals half, it's going to be halfway in between. T equals 2, probably be this one. You can check that if you want. if I put t equals 2, I get 1, 4, which, yep, that's that point. So I'll, t equals 0, this is my starting point, and I'm just moving along the line as t gets bigger and bigger. If I made t negative, it would go in this direction down here. One thing you might notice is, I made this my starting point for t equals 0 because that's the point I was given, right? The original point. I didn't have to. I could have started here. So my vector equation is not unique. This point can be any point you want as long as it's on the line. As well, this direction vector could be any direction vector. I just chose this one because it's sort of the lowest terms one, right? I could have used 4, 2, or 3, or sorry, 6, 3, or whatever. Negative 2, negative 1. You could use whatever you want. Okay, so that's a vector equation. I'll just formally define that right now. Okay, so a vector equation just pause it and write it down. Okay, so here's my formal definition. If you have a point on the line, a1, a2, and a direction vector m1, m2, then the vector equation of the line is xy will be equal to the point plus t times the direction vector, where t is some scalar, some real number. And then sometimes we'll write this, instead of writing xy, we'll think of xy as a vector. So we'll call xy r, so you just say r is equal to a1, a2 plus t m1, m2, where again t is a real number. Okay, so that's just another way of writing it. So this is a vector equation. This also leads to the concept of what we call parametric equations. So parametric equations, very easy if you understand vector equations, is just the components of the vector equation. So in R2, there's two components, right? An x component and a y component. So you're going to have one equation for x and one equation for y. The x equation in this case would be a1 plus t times m1, and the y equation would be a2 plus t times m2, where t is any real number. Okay, so that's parametric equations. So you have vector equations, and then related to that, parametric equations.